Dijkstra's algorithm is a must-know if you're currently prepping for coding interviews. In this video, I'll walk through a Leetcode problem utilizing Dijkstra's algorithm and show exactly what's happening in the data structure as we traverse through the graph. So the problem we're going to be looking at today is Leetcode 2976. In this question, you were given a source string and a target string. The goal is to convert the source string to the target string by changing each letter. There's different costs to change one letter to another. The cost to go from one letter to another is represented by three arrays: the original, changed, and cost arrays. The cost to change from an element in original to an element in changed is denoted by the element in cost within the same index. These arrays represent a graph with different paths to each node, where the nodes represent letters. Let's consider the following example of these three arrays. They would represent the following graph. The very first thing you need to do when trying to find the shortest path in a graph is construct an adjacency list for each node. This will be a dictionary in which the key is each node in the graph and the value is a list of all nodes that are directly adjacent to it. We could initialize the adjacency map like this. However, you'll see why this is actually a mistake in a second. A convenient way to build the adjacency maps is by using zip. This allows us to iterate through all three arrays at once as shown here. What we would like to do is just append the neighbor node to a list of neighbors. However, if we were to do this now, we would get a key error, since we're calling a key that doesn't exist. So this is why you actually want to initialize the adjacency map using default dict and passing in a list. Using default dict means that now when we call a key that doesn't exist in the map, it will create an empty list to which we can then append the neighbor to. Now we can build the adjacency map, which looks like this. Once the adjacency map is made, it's now time to build the actual algorithm. Dijkstra's algorithm accepts a starting node, and we will return a dictionary with the minimum cost, or shortest path, to reach every other node from it. The algorithm starts by initializing a heap. If you don't know what a heap is, it's basically a very efficient data structure for retrieving the minimum of different elements. The minimum will always be the head of the heap, and in the same position. This allows the minimum to be obtained in O of 1, or constant time. In this case, each element in the heap will be a tuple, in which the first index is the cost to get to the letter. This is what the heap will use to sort by, and the second index is the letter. We then initialize our min-cost map, which is what Dijkstra's algorithm will return. Now if you don't understand this next part right away, don't worry. As we walk through it, it'll become more clear. There's also slightly different ways to code this, but here's what I believe to be the easiest to remember. We start with the while loop, which checks if there's still elements in the heap. We then pop from the heap. Popping returns the head of the heap, which is the minimum, and it also removes it from the heap. When we pop from the heap, that represents the minimum cost to reach that node, so we then add it to our min cost map. We then push the neighbors of the node we just popped to the heap. We then return the min cost map. So let's actually walk through this example step by step to see what happens here. And there's actually a line of code in the algorithm that I intentionally left out, but I'll show it later as we walk through it along with why it's needed. Starting with the source node of A, so far our min cost map just has A with a cost of 0 since it's our starting node. We then push each of its neighbors to the heap with their cost. Node B makes its way to the head of the heap since it's cheaper to go there compared to node E. After we push the neighbor nodes, we start the next iteration of the while loop since our heap isn't empty yet. We then pop the head node, which is B, and add it to our min cost map, since we now know the minimum cost to get to B. So we then head to node B and push its neighbors to the heap. But remember, we need to push with the total cost. So for node E, we add the cost from B to E to the cost to get to B. The shortest path moves to the top, and we then go to the next iteration, pop from the heap, and add it to our min cost map. Now we go to C since we just popped it, push its neighbors to the heap, and pop again. However, what happens to the heap in this case when two other nodes are tied for the minimum? In the case of tuples, it actually sorts them based on the second element lexicographically, so node D would actually move to the top here. We then head to E, since that's the node that was just popped, and push its neighbors to the heap. However, E doesn't actually have any neighbors, so nothing gets pushed here. We then pop again, which brings us to node D, and push the neighbors. this point, we've already found the minimum cost from A to all other nodes, so everything in the heap represents non-optimal paths for nodes we've already seen. This is why when we pop a node that's already in our min cost map, we just continue and ignore it. So now everything else gets popped from the heap since we've already solved these nodes. And that's the whole algorithm. Now that we have a way to get the minimum cost to every other node given a source node, we just need to apply Dijkstra's algorithm to every unique letter in the graph. After doing this, we now know the cheapest path from every node in the graph to every other node. So now we just initialize our cost to convert the string as 0 and begin iterating through the source and target strings using zip. If the target isn't in the minimum cost map for a given letter, it means it's not possible to convert to that letter. So in this case, we would return -1. We then just add the minimum cost to go from the source letter to the target letter and return the answer. So this video took a while to animate, and I hope the visualization of what the heap and graph traversal looks like helped. Leave a like if you enjoyed, learn something new about coding every day, and see you next time.